these are the summary of what we have done during the last lecture. Formation of a single particle of mass m about a fixed point, in which the distance of the particle to the fixed point is not changing. It's a rigid rotation. Now, these results about the rigid rotation is mainly applied to the rotation of a diatomic molecule. So let us see how that happens. So rotational energy levels of a diatomic molecule. Now, the diatomic molecule has two atoms connected by a bond. Let us say this is mass 2, and this has mass 1. There is a point called center of mass. The center of mass. Now, let us consider the rotation of such a diatomic molecule about the center of mass, which means during the rotation, center of mass is not going to change. It's fixed in space. Now, if the rotation is like that, then this mass is moving in this manner. This is the center of the circle. And at the same time, this mass is rotating. The rotation of the two masses is in concert, which means they are moving together. So when this mass moves during the rotation, this is also moving. The rotations are not independent, but together. They are synchronized. We are assuming that during the rotation, the bond length is not changing. This distance is fixed. Of course, in reality, in a real diatomic molecule, the bond length is not really constant, but it's also changing. But here, we are assuming that during the rotation, the bond length is fixed. So this is why we call it rigid rotation. Now, by definition of the center of mass, if you call this distance from the second mass to the center of mass R2, and this is from mass 1 to the center of mass S, R1. From the diagram, it's clear that there is a relation between R1 and R2 such that the sum of the distances is equal to the one length. This is one relation. Another relation between R1 and R2 arises from the definition of the center of mass. It is mass 1 times R1 must be equal to mass 2 times R2. This is definition of center of mass. This means that if the second mass is larger than the first mass, the center of mass lies nearer to the larger mass. If the two masses are the same, center of mass is exactly at the midpoint. These concepts you should remember from your physics course. Now, the given information, data about this problem is the one length is given. This is given. And also, mass 1 and mass 2 are given. For example, if we consider hydrogen chloride molecule, we know the mass of hydrogen, we know the mass of chloride metal. And also, we look up for the one length. So these are the given data. Now, using these two relations, we can express R1 and R2 in terms of the masses and the one length. We have first mass is mass 2 over total mass times R0, and R2 is mass 1 over total mass times R0. That is capital M, and 1 plus M2. It's the total mass of the diatomic molecule. Now, the moment of inertia of the molecule about the center of mass is, by definition, mass 1 times R1 squared plus mass 2 times R2 squared. This is the moment of inertia. You see, if this plane is the xy plane, then the z direction is perpendicular to the black body. And definition of moment of inertia is it's a sum of mass times distance squared for all particles. The distances should be perpendicular to the axis of rotation. So here, because the axis of rotation is the z-axis, the distance of mass 1, of mass 1, so the z-axis is R1, and that of mass 2 is R2, and it's a sum. Mass 1 times distance, perpendicular distance squared. You can generalize this, and you probably know it. If there are large atoms, you can say polyatomic molecule, then same definition applies. Mass of each particle, each atom times the square of the perpendicular distance to the axis of rotation and just add up such terms. It gives the moment inertia of the molecule. In our case, this is a diatomic molecule. We can use, we now get rid of R1 and R2 in terms of R0. So we use these two connections and then simplify the result. We obtain the following. Using this expression for R1 and that expression for R2, we obtain this result, where mu is called the reduced mass. It's from here you will see that mass 1 times mass 2 divided by mass 1 plus mass 2. This is called reduced mass. It has mass unit, of course, because here in the numerator you have square of mass unit, but there is a first power of mass unit in the denominator. Therefore, the net unit is mass unit. If you are using kilograms, the net unit is kilograms. Why is it called reduced mass? Because the number you obtain from this expression for any M1 or M2 value, all right, is necessarily smaller than either M1 or M2. For example, if we calculate this for hydrogen chloride molecule, say in gram per mole, hydrogen is 1 gram. Chlorine is, I think, 35.5, something like that. If you substitute these numbers to this expression, the value for mu is going to be smaller than 1. For any two numbers, M1 and M2, the value you calculate from this expression is going to be smaller than this answer. So, in that sense, it's called reduced, because we know the meaning of reduced. Because it's a mass, but this mass is smaller than either mass. Okay. Now, in this problem, we are talking about the rigid rotation of a single particle with mass m. And it was rotating on the surface of a sphere. This was, and then, well, try to visualize that this is not a circle, but it's a sphere. And we have a particle here with mass m, and this is rotating. Its motion is always on the surface of the sphere. And its distance to the origin is fixed. It's equal to R0. Okay, now, the motion of a diatomic molecule that we have pictured over there is equivalent to the motion of a single particle, like this one. The rotation here is around the center of mass of the diatomic molecule, such that the bond length is not changing, it's fixed. Always equal to R0. The simultaneous rotation of the two masses here is equivalent to the rotation of a single particle with mass mu. You see, even though we have two particles, because the rotation is in concert, the rotation is taking place simultaneously. When this particle rotates everywhere, the other particle is also rotating like that. So it's a together rotation. And in that sense, it's equivalent to a single particle. But the mass of the particle, which should be taken, is not either m1 or m2, or it is not m1 plus m2. It should be this reduced mass. Then everything, you can apply these expressions directly to the rotation of a diatomic molecule. Now, in doing this, there is a change in the notation. These symbols, notation in the quantum numbers, the others are the same. The L symbol and the small m symbol, they are left for general rotation. But when we apply the same ideas to the rotation of a diatomic molecule, chemists use some other symbols for the quantum numbers. They use instead of the L symbol, capital J symbol is used. Everything's same as before, just the symbol for the quantum number is different. This is for chemical reasons. Chemists are used to using such a symbol. So here also use J. Now, instead of the small m, they use capital M symbol. But everything is, of course, same. So m is between plus j and minus j. So you will write here 2j plus 2. So J and M symbols are employed. For rotational energy levels as states of diatomic molecules. All right, let us now then summarize both the energy levels of a diatomic molecule and also the rotation state functions using an energy level diagram. It is increasing energy. is 0. Now, according to our expression, the lowest energy is for J equals 0. So there is a energy level at 0, which we indicate by this expression. This is for J equals 0. Notice that when n changes for a given J, energy is the same, because this expression doesn't contain n. On the other hand, this rotation state function, there are 2 times J plus 1 different n values. It means different rotation state functions for the same J. Same J means same energy here. But when J is larger than 0, n will have more than 1 value. For J equals 0, we have just 1 n value. What is that? N equals 0. So, degeneracy of a rotation energy level G sub J. For a given J, it means a given rotation energy. Number of state functions, number of rotation state functions is equal to 2J plus 1. When J is 0, this number is 1, which means non-degenerate. Now, the next energy level is when you put J equals 1, then you get 2E. This is the first rotation excited energy level. We indicate it by a dash. This is for J equals 1. What is the degeneracy of this rotational level? From this expression, 2 times 1 plus 1. So it is 3. The subscript is J subscript. The next energy level is when we put J equals 2. 2 times 3, 6. This is for J equals 2. And how many states are there? 2 times 2 plus 1. There are 5 states. Now, in such energy level diagrams, when the degeneracy is not high, we use, for instance, for this level, we draw 3 dashes, which are on the same energy level. Each one is separately indicating a state. But in this problem, because as the energy goes up, the degeneracy is increasing. Say, even at this point, the degeneracy is 5. So drawing 5 dashes next to each other makes the figures cumbersome. So, for that reason, we just draw, in such cases where there is high degeneracy, we draw just 1 dash indicating the energy level, and then give the degeneracy by a number, like this. Let us indicate one more energy level. The next energy level is when you put 3. 3 times 4 is 12. So here is 12E. This is for J equals 3, and degeneracy of this level is 7. We can continue like that to show all of the energy levels. All right, I have exercise about this. Let us consider carbon monoxide molecule. Carbon monoxide. Now, carbon has several isotopes. Carbon has the most abundant carbon atom is carbon 12. But there is also carbon 13, carbon 14. The B value contains the moment of inertia. But to calculate the moment of inertia, you need the masses. Right? Now, it turns out that experimentally, very small differences in B values can be distinguished experimentally. For that reason, when you apply these ideas to the molecules, it is important that you should indicate which isotope of the atoms are present in the given molecule. If I just write it like this, then it would mean average mass for carbon and average mass for oxygen. Okay, but the information about rotation energy levels is obtained experimentally using microwave spectroscopy. There is such a technique, microwave spectroscopy. And the experiment is done very crudely like this. You have a container. You have, say, carbon monoxide gas in it. In the gas phase, of course. Then radiation is sent to the sample, light is sent, but the frequencies which are used are small frequencies in the microwave region. And then the emerging light is analyzed whether photons are absorbed by the molecules inside the sample or not. Now, the sample is of course a macroscopic sample. There are Avogadro's number of molecules. It contains, in the natural abundances, all isotopes of carbon and oxygen which form a molecule. For example, the most abundant will be carbon 12 isotope and oxygen 16 isotope. But the sample will also contain carbon 13, forming a bond with oxygen 16. All of them are in relative abundances. Now, the experiment can distinguish between such isotopically different molecules. For that reason, whenever we do some calculation for, say, B value, we use the correct isotope masses. So my calculation is going to be for carbon monoxide molecules in which the carbon atom is carbon 12 isotope and oxygen atom is oxygen 16 isotope. The bond length in carbon monoxide molecule is 112.8 picometer. It is important that the bond length does not depend on isotope masses. In other words, what did we say? For this molecule, carbon monoxide, in which carbon is the carbon 12 isotope, oxygen is oxygen 16 isotope. The bond length is 112.8 picometers. If we take, say, carbon 14, this molecule, in which carbon is carbon 14 isotope, the bond length in this molecule is the same as bond length over there. So when the isotope changes, the bond length doesn't change. That's something you should remember. Okay. All right. Now the masses are, of course, we look up the isotopic masses. You shouldn't go to the periodic table, because the periodic table gives the average masses. You have to look for isotopic masses. Most physical chemistry textbooks give you a table for important, for the isotopic masses of important elements. Now, I look up masses. Carbon 12 is by definition. This is exactly 12 atomic mass units. Or, as you know, that number means gram per mole. Now for the oxygen 16 mass, it is 15.9949 atomic mass unit. Now, we first calculate the reduced mass using these numbers. 12 times 15.949 divided by the sum. And you use your calculators, you will get 6.8562. What the units for these numbers are atomic mass unit. So here unit square in the denominator with unit to the first block, very simplified. This is atomic mass unit. You see this number 6.8 smaller than 12 and also smaller than 15.99 reduced mass. The number is smaller than either of the atomic masses. In our calculation, we should use SI units. So the conversion factor atomic mass unit, either you look up what is 1 U is, or if you forget, it is just remember it is gram per mole. So change gram to kilogram, and for mole you put Avogadro's number. That's the conversion factor. And when we do the calculation, we get 1.1385 times 10 to the minus 26. we have a number for the reduced mass. The bond length is also given to us. So we use the definition of moment of inertia. Moment of inertia is reduced mass times R0 squared. Reduced mass is given over there. 1 times 112.8 kilometers, which is 10 to the minus 12 meter square. And if you do this calculation, then you get 1.4486 times 10 to the minus 46. What is the unit? Kilogram from here times meter square. Then we calculate the rotational constant E. What was the definition? H bar squared divided by 2 times moment of inertia. You take either the value of H bar directly from data section. What was the definition of H bar? H divided by 2 pi. H is 6.626 times 10 to the minus 34. H bar is 1 point something after division. You take the square of it and take this number and use it there. And you calculate this. E is 3.8386 times 10 to the minus 23 joule. This is the value of the P. Now, this number will change, even though slightly. If you use a nickel isotope, if you use, say, carbon-14 here, the bond length is the same, but because the reduced mass is slightly different, the numerical value of B is going to be different from this one. What I'm saying is that experimental techniques are sensitive. They can, the technique is capable of knowing the difference between the B value of, say, carbon-14 oxygen 16 from carbon-12 oxygen 12. So it is important that isotopic masses, correct isotopic masses should be used for the in calculations. Now, let us directly apply this for continuing the application. Suppose that there is a carbon monoxide molecule. One of those carbon monoxide molecules is initially in the J+2 state. Here. Initial state. Then, microwave radiation or light in the microwave region is the sample is exposed to such a microwave light source, and that molecule initially in the J+2 level makes a transition to J+3 level. And the question is, what is the wavelength of the photon required, which will cause such a transition? Now, how much energy is needed to make this transition? You see the numbers. You tell me in terms of V symbol. Initially, that energy, final energy is this one. How much energy is needed from outside? 6p. 12p minus 6p. This is delta E. Now, this is the energy change in the material particle. Now, where is the source of this energy? It is the light source. So we have a light source, microwave radiation. It contains microwave photons. If the energy of a photon that we are using is exactly this number, then that photon is going to be absorbed. So, this is photon or light. V is this value, and we can first calculate the frequency of the photon. I don't have the number for the frequency, but I have directly obtained the wavelength because the question is asking for wavelength. We can calculate directly H times C is 60, and this one 8.625 times 10 minus 4 meters. This is the wavelength of the light, which will cause the molecule initially at J equals 2 level to make a transition to J equals 3 level. Okay, let us start here.